Good afternoon. We will start our last session of batteries, which is just basically session two. And hopefully, you've had enjoyment with the batteries and the harmonics of this session. So, let's get started. So, last week we talked about basic battery principles and had a brief overview with some of the testing. And today we're going to have a short review of that, more in depth of each part, and we'll talk a little bit about the actual uh, testing, discharge testing, or load testing of batteries. So, to review, we talked last week about the visual inspection, and the visual inspection is very important. It's done on a monthly basis, uh, but you're looking at everything with regard to that battery system. You're looking for cracks in the case of that battery system. Obviously, you're looking for any leaks, corrosion to be noted around the connections. That's where they typically start, but they can also come, or that the corrosion can also start around the post of the battery where it leaves the case. Uh, you can find these problems before they become catastrophic failures. Uh, Now, there are some things that you just can't do much about if there's a crack in a battery case, obviously, but we are here to make sure that we have a reliable battery system and that the system functions when it's needed. So, that visual inspection, while necessary, really doesn't tell us anything about the state of charge of the battery, or it doesn't tell us anything about the capacity left in that battery, nor does it tell us anything about the state of the actual health of that battery. And we need to understand that we can have a battery that's not fully charged, that would have reduced capacity, but still might be of reasonable health. So we need to be able to discern between those three various components. Second of all, let's talk about voltage testing. Float voltage, and we talked about the float voltage last week of a typical lead calcium battery, 2.25 volts per cell. If the system float voltage is lower than that, or if a single cell float voltage is lower than that, then that's the indication that that cell or that string is not fully charging. And so if it's not fully charging, it cannot supply full capacity as needed, as designed for use. So that's a concern. It could be an indication of sulfation on the plates, which is the white powdery stuff that you would see on the plates itself. If you have a high float voltage, that's an indication of overcharging. Uh, this can lead to increased grid corrosion. It will increase to higher temperatures in the battery. And as with all electrical equipment, temperature is an enormous enemy. So we don't want a high temperature on these batteries. Uh, but that voltage testing, whether it be string voltage or individual cell voltage testing, uh, tells us very little about the state of the charge uh, and the state of the capacity, but it tells us also not a lot about the state of the health of the battery. Current. So this is the current that the charger is putting out during a float condition, our standard idling position of the battery. A high float current could be a precursor to thermal runaway. Whether in thermal runaway is a situation where uh, the temperature would increase in the battery or a battery cell, and it would just continue to increase and require more and more current, and it's a deadly spiral. It could also indicate that there may be a short circuit or a ground fault on the system. It could be a sign of a high float voltage. If your float voltage is normal but your float current is high, then there's something definitely wrong there. Once again, it shows something that's wrong, but it doesn't really tell us about the capacity of that battery string or the health of that battery. Then another one of the tests that we didn't talk about last week is ripple current. Uh, and to understand what we mean by ripple current is typically batteries, well, not typically, but batteries are DC systems. So I would expect the voltage to remain constant. That should be a straight line. I would expect the current to also remain constant, flat line, I would not expect to see any sinusoidal waveforms on the voltage or the current. But if we were to read with our clamp-on ammeter and put it on AC and see some sinusoidal waveforms on that current, that's an indication that we've got some issues. The issues there, if we see a lot of ripple current, that's more a issue of the charger. That's definitely not an issue with the battery. So that would be an indicator that we've got issues with the charger, and we should be concerned about that and follow up on that. Temperature testing. Temperature is critical for batteries. High temperatures reduce batteries, okay? Again, it's not an indication of the capacity or the health of the battery, but it is an indication of the conditions that the battery has to operate in. So a temperature is important for us to do. Now, here's one we want to talk about, specific gravity, okay? We're taking specific gravity measurements. And specific gravity actually reads the ratio of the density of a liquid to the density of water, okay? And the density of the acid that's inside here is higher than water, so it should be higher than 1. Specific gravity measurements in batteries indicate how much sulfate is in the electrolyte. So it provides information about the state of charge. So this is one that really gives us a great indication of the state of the charge of each cell if we're going to take specific gravity readings of each cell. But it doesn't really tell us about the capacity of the string or the health. Now, one thing about specific gravity, it is temperature corrected. And we'll talk about that a little bit later. But it's temperature corrected, so we have to take actual temperature readings. And during certain sessions, especially in the annual test of the battery, when we take specific gravity of each cell, we have to take the temperature of each cell. And it is temperature corrected to 77 degrees Fahrenheit, or it would be 25 degrees Celsius. So everything would be converted back to there, so we could actually compare one reading to the next reading, for historical data. Then we do impedance testing. And I can see right now that I've negated to take into account the connection resistance of the connections between one cell and the other. But that's not a battery indicator, that is a connector indicator. But impedance testing. We can take and we need to do impedance testing of each cell of the battery. Or in the case of a 3-cell unit, so maybe 3 cells if we can't get to individual cells. It is an indicator of the health of the battery, okay? But it does not measure the capacity of the battery. So again, it would be an indicator of some health, but not an indicator of the capacity. And finally, we talk a little bit about discharge testing, okay? So discharge testing is the only form of test that will determine the actual capacity of the string. So nothing else that we can do will actually tell us of the actual capacity of this battery rather than the discharge test. So it is a vital test to perform. Remember, we don't test it all the time. We don't test it annually. It's going to be, we want to test it after its battery's been in service for about a year. And then usually at certain segments after that. Some companies prefer to do it like every 4 years, some every 3. A lot of people like every quarter of what the battery life expectancy is. But the only way you can actually tell the capacity of the battery is by discharge tests. So let's talk about some typical values. Typical float values. We mentioned these briefly. Flooded and vented, the sealed batteries, both 2.24 volts per cell for lead calcium. If it's lead antimony, 2.17. For NiCad, somewhere between 1.41 and 1.44. You'd look at the manufacturer specifications for that. Typical equalized voltages: lead calcium, 2.35 volts per cell. Lead antimony, 2.28 volts per cell. And NiCad, you're going to have to see the manufacturer specifications. Now, again, we talked about all of these last week. Float is where we normally are. That's where we're idling. Equalize is when we have a float voltage of a cell that's getting too low. And then the final thing on this sheet is the specific gravity. So when we talk about specific gravity, lead calcium, we want that specific gravity to be somewhere between 1.21 and 1.3. Again, that's the ratio of the electrolyte that's actually in there as compared to what it would be if it was actually just water. And it has to be temperature corrected. And again, temperature correct is 77 degrees Fahrenheit, 25 degrees C. So that's an important test for us to take. So voltages and specific gravity of each cell. Now, when is corrective action needed? So here are certain items that are pretty easy. You can tell on the visual inspection on the first one. If the electrolyte reaches the low level line, okay, so you get a high and low range for the electrolyte in the battery. That shows us that we need corrective action. Now, since that's the first thing basically we're doing is a visual inspection, understand that if we're going to test that battery, all the tests have to be completed before you add electrolyte, because it's going to take the battery a while to take that new electrolyte and get it charged and all those sorts of things. If you see post or terminal corrosion noted, that needs to be taken care of. Now, unfortunately, in some of the designs and batteries now, that may require an outage of that battery to restrap that battery. Some of the older batteries and some batteries will give you 2 terminals per post to be able so that you can actually restrap it while it's in service. Here's the big one. If the float cell voltage varies from the average cell by more than 0.05 volts for lead calcium, 0.03 volts for antimony, or if it's less than 1.35 for NiCad, you need to equalize charge that string for at least 24 hours. So what does that mean to us? Well, let's look. Well, I got a couple more slides here. Corrective action required. Intercell terminal connectors. So the connections between one cell and the other. Again, we want to go with the historical data if we possibly can. So the historical data, if it varies by more than 20% from what it was day one, that's a need for doing something about those connections. Or if it's above 50% above a similar connection, that's reason to be concerned and require a specific corrective action. Now, if a cell impedance should not vary by more than 25% of the cells, so they should be relatively constant, or some manufacturers will actually even specify what the cell impedance requirements are. And then the big one that we're going to mention here, just for this point in time, is the voltage from positive to ground is not nearly equal to the voltage from negative to ground. We talked about that last week, that substation battery systems are ungrounded systems. And one thing that is of immediate concern is if we do have a ground on that battery. First ground will still permit the battery to function. But the second ground means that we've got real problems, that it's not going to function properly. So let's look at some calculations, okay? So let's say that we've got a 60 cell battery, lead acid. So we talked that our typical float voltage is 2.24 volts per cell. We got 60 cells. And so that battery is going to be operating at 134.4 volts. Now, again, last week we talked about, we call this a 120 volt control battery, but it's operating almost 15 volts above that. So some people have had a little problem. Back in my utility days, we burn up a lot of indicating lights on panel boards with 60 cell batteries. So we actually went to 58 cell units, which made the float voltage 129.9, which was a little easier on our lighting and indicating lights inside the system itself. So let's look at this. If any one of our batteries, let's just say that the overall string is operating at 134 volts, That's good. That means it is running at 2.24 volts per cell. That's good. We've done a reading. But if any one of our individual cells are at 2.19, less than or equal to 2.19, or greater than or equal to what? 2.29, that's an indication that we've got an issue. If it's less than or equal to 2.19, we need to have an equalized charge so we can try to get all those batteries back to the same voltage. If it's greater than 2.29, that means that something has happened and we've got another one there that is less than that. So again, it's an equalized charge. We got to find the one that is less than. So the equalized charge would be for this battery 141 volts. So sometimes you might not want just to leave that equalized charge on for an extended period of time. It might take more than 24 hours to actually get the things leveled out or equalized. And you might not want to just be putting that kind of current and voltage on all the cells. So you can purchase a single cell charger and just strap across the one cell and raise the voltage of that one cell to 2.35 volts till you get it to bring it up. So that's a possibility. Okay, specific gravity temperature correction, okay? So this is Fahrenheit, and we can see it's 77 degrees right there, 77 degrees Fahrenheit, 25 degrees Celsius. That is temperature correction of 1.0. So there's some basic numbers like you change it like 0.03 per degree change, but the charts are readily available, so just use the chart to make the corrective change, and our software will make the change for us. So let's go to some myths about battery capacity tests. Myth number one, capacity testing ruins the battery and is expensive. Well, it may be a little expensive and a little cumbersome to do, but it's the only way that you can truly understand the capacity of your battery, and it does not hurt the battery if performed properly. Myth number two, a battery must be equalized before testing. That's not necessarily true. Some manufacturers suggest that, but typically we do the battery as found because that's the condition that we want to really know. Myth number three, stop the test when the first cell reaches the cell in voltage. So basically we'll talk about that cell in voltage. For a lead calcium battery, it's 1.75 volts per cell. Remember, it's supposed to be running at 2.24 volts per cell. We say that when it gets to 1.75 that it has done everything it's going to do. So some people say when that first cell gets there, we stop the test. That's not necessarily true, and that's not what we do. That's not what the IEEE standards say. There will be differences in cell impedances on cells with higher capacity and failed cells. That is also false. Those are the ones that want to tell us that cell impedances are everything we need to have. The cell impedance is a valuable test, but it does not give you a capacity test. Capacity test continued. Verified battery has not recently been discharged. That would be important. Okay, we want that. Check all battery connections and ensure that resistance readings are correct. That's correct. We want to make sure that we've done everything else in our testing process. We want to record specific gravity of every cell, record the float voltage of every cell, record the temperature of every 6 cell to get an average temperature, and record the battery terminal voltage, okay? So we're doing this, and as a matter of fact, most of these things are monitored during the test itself. So how do we go about this test? Well, we have to disconnect the load. There's the big key. There's the big key. So when customers or individuals talk about that it might be expensive, well, the expensive part is this is a substation battery. We really can't disconnect the load unless you shut the substation down. And typically they don't want to do that. But some utilities actually do shut substations down for a period of time, like every 5 or 7 years for complete maintenance. But if the substation is not shut down, you need to bring in a portable battery because the substation still needs to be able to function. So you're going to disconnect the load. Then you're going to disconnect the charger. This battery is on its own. You start the discharge. You record the voltage of every cell and every battery terminal voltage in the beginning of the discharge test, okay? You do that. You record the voltage of every cell and the battery terminal voltage during the test. That means you have lots of leads to connect to this battery, okay? Maintain the discharge rate until the battery terminal voltage to the end discharge voltage of 1.75 volts. Now, that's not on a single cell. We'll bring about that in the future, but that's the total voltage. So if I have 60 cells, I have to do the math. If I have 60 cell batteries, 60 times 1.75 would be 105 volts. For a 60 cell unit, when the overall string voltage got to 105 volts, that's when I would stop the test. I would consider it totally discharged. Now, you can see why I wouldn't want any load on that thing, because I would not be able to do everything I need to do inside the substation with operating breakers and those sorts of things with the voltage being so low. Record the voltage of every cell and battery terminal voltage at the end of the test and calculate the actual battery capacity. So those are the steps of doing the capacity tests. Now, it requires research, research, research. Probably the most difficult part of the task is to find the actual battery manufacturer information. Here's a case where we've got some batteries where we've got the actual battery type, their model number there, the type, we've got their part number, and it will tell us, it's like if you want discharge for 5 minutes, 10 minutes, 15 minutes, a lot of people want the 4-hour discharge. So it will actually tell you of what kind of current, constant current discharge, what kind of current that you should be drawing in order to monitor this discharge. And so we would set up our test set. If we were doing a 4-hour test for this TOPS battery, we would set it up for a 40.5 amp discharge and make sure that it was consistent at 40.5 amps. And then we do the monitoring of all the cells during that process. When you do calculation of capacity, you have to take temperature consideration of initial temperature. And so the initial temperature of the battery is taken into account in degrees Celsius, and there's a constant there that you would use. So there's the equation where percent capacity at 25 degrees. This is at 25 degrees C. And the actual time of the test to be specified is TS. TA is the actual time that we did, and KT is that temperature correction. So this is how long it said it should take. Remember, that was a 4-hour test a while ago. So if it's supposed to take 4 hours, but it only took 3 hours and 30 minutes, then we would operate this, do that calculation, we'd find out what the actual capacity was. So a few more notes. Stop the test at 1.75 volts per cell for the 60 cell string. That equals 105 volts. We already discussed that. Do not stop the test when a cell gets to 1.75 volts. Continue on. I'm looking for the string voltage to be 1.75 volts per cell. Stop the test when any cell gets to 1.0 volts. So I wouldn't stop it when it got to the end voltage, 1.75, but if it got down to 1.0 volts, I would have to stop the test, because what I do not want to do under any circumstances, I do not want the polarity of that battery to change. That's a difficult problem to resolve. So you have 6 minutes to jump around that cell and continue on the test. We don't like that option, but you have 6 minutes to jump around that cell. Basically, we would just stop at that point, tell the customer if they've got a real problem with that one cell. We'd be looking at other cells as well, see if they were doing the capacity, if they were on the capacity curve for the battery. So we have some knowledge here. What actually happens is that when you start this capacity test, and Kupdi, whoever that is, this was his theory and his idea, but when you look at the voltage, when I first start that capacity test, discharge test, there's a huge drop in voltage, and then it will climb back up, okay? And so we expect to see this drop, but this is the linear range that we want to see. And we can see right here is when it stops to being linear, and that's when it's going to drop off pretty quickly. So that is a typical curve of what it would look like. Now, if you look at the overall discharge for an 8-hour discharge, this one's 8 hours, we can see that little spike very early on, okay? And this is 250 volts. It's a 265 volt system down to 250 volts. I mean, we see it gradually drop off. And again, this is about a linear line. It's almost a line. And this line is supposed to be the current that's drawing. Obviously, it's not on the right scale, but we're seeing a constant current being drawn at the time. So here's our sample test sheet that we have, that we've done in the past. So I actually have the name on here, but this is not a capacity test sheet. This is just a typical test sheet that we do. So we look at each cell, and the voltage at each cell, the cell resistance, that's the impedance of the cell, and we see the strap resistance. And so we can see the overall float voltage was 134.8 volts. So that was just a little bit high, not much. So what is that 134.8 volts? 134.8 divided by 60 cells is 2.246. So that's 2.247 volts per cell. So if that's the case, anything less than 2.197, less than or equal to that would be a real kicker for me. So we can look at this, and I can see, looking down the string, that I don't see anything close to that, okay? So I don't see any indication. Then I look at the actual strap resistance. I see strap resistance are pretty common. Every once in a while I see one that hits 1,000. But if I go down to the bottom here, I see some different strap resistances. Maybe a little longer strap for some of these, but typical. So if I look at the whole battery, here's the summary. The high cell voltage is 2.25. The low cell voltage is 2.22. That's well above. So that's a good range in between there. So I'm not over 0.05. If I look at the impedances, relatively close. Strap resistance, pretty close as well. So that's a good overall test string that we have. So that's the end of batteries 2. So if you have questions, give me a call, and look forward to seeing you in a future Lunch and Learn. Take care and have a great day.